All right, so our next section, our last section of this chapter, and honestly probably the easiest one, is we're going to start working on cylindrical and spherical coordinates. And the reason why we do is twofold. A lot of times when we're dealing with specific shapes like cylinders and spheres, we can redefine these rectangular coordinate systems, x's, y's, and z's, in terms of other coordinates that make our equations way easier and way nicer. You're like, well, okay, what's the big deal? I'm used to x's, y's, and z's. That's right, you are. And so when we go to graph them, typically we do x's, y's, and z's because we're not used to these other ones. The more we get used to these, the more other shapes become easier. Furthermore, when you get to the actual integrals, you are used to integrating across a straight line, the x-axis. We are going to start integrating across regions that have areas. And the easier we can define those regions, the easier our integrals become. And we're going to be using cylindrical and spherical coordinates to do that. So in chapter 14, like 3 chapters from now, when we actually get there, we're going to be relying on your knowledge from right here. We do it now so that some of our other stuff becomes easier when we have to graph in the next chapter, and the one after that, and the one after that. But when we finally get to like double integrals, triple integrals, this is going to save your life. It's going to make really hard integrals easier, at least easier. I'm not going to say easy, but at least easier. You guys understand the idea behind doing it? That's the idea. Now, how it works, we're going to start with cylindrical coordinates, and we're going to take off and do spherical. Cylindrical coordinates, they literally are just like polar coordinates. Do you remember polar coordinates? Section 10.3, I think, from Calculus 2. Polar coordinates. Maybe 10.4. No? 10.4. One of those two ones. Polar coordinates, they're not the same thing as rectangular, x, y. What they did was they said, I want to give you an angle to the x-axis or the polar axis and then shoot you off, just like that, a radius. That's what they did. It was on the xy plane, though. Do you remember that? It was a projection on the xy plane. This is just like polar on the, please listen carefully, I don't want to lose you. Cylindrical deals with r and theta, and it's still on the xy plane. That's this one. It's just that we have to add a z component. So what's going to happen is we're going to have this polar representation on the xy plane and say, hey, right where that is on the polar coordinate system, right where that is, we're just going to take that and raise it up along the z-axis. That's how cylindrical works. It is polar with a z component. Let me show you. So here's polar. Polar's on a plane. Polar is on, typically we think of the XY plane. It was just a projection onto that XY plane. Polar had R representing the radius to whatever, away from the origin that we have, and theta is the positive angle from, or negative angle, but it's the angle from the polar axis. We think of the x-axis. It's still the x-axis. If we want to change the cylindrical, it's even the same order. We still have an r, we still got a theta, but now we have something that gives us this 3D coordinate system that's not the xyz coordinate system. It's r, theta, and z. What's even better, even more better, what's even more better about this is that all the stuff that allowed you to translate from rectangular to polar, since the z is the only new thing, it all still works exactly the same. The z just says, hey, you're on the polar. Now you're lifted up on the z, or you're pushed down on the z. So all the stuff we use to translate between rectangular and polar is exactly the stuff we use to translate between rectangular and cylindrical. And you're going to like it, because the z coordinate just doesn't change. Z is z. You'll see it. So the same identities hold true. Same stuff for both of these. Now, if you don't remember them, you can always think back to some trigonometry and do some right triangle trigonometry to get these. But x was always represented as r. Oh, do you remember x? Cosine. That's right. Y, come on.
R sine.
Beautiful. So check it out. Here's what I'm talking about. In 3D, in the R3 coordinate system, we have x's, we got y's, we got z's. We've got a way to translate x's, it's r cosine theta. We've got a way to translate y's, it's r sine theta. Do we need to translate z's?
No.
No. The z is the z. The height is still the height. That's really nice. That's what I'm talking about. The polar changiness is the cylindrical changiness. Z, just let z equal z. It's still giving you the height above the xy plane. This z is giving you the height above the xy plane. Same z. Head nod if you're with me on the same z. That's pretty cool. It's pretty easy to do. We use these identities to go from cylindrical to rectangular. You plug in cylindrical, you get rectangular. So this is used for cylindrical to rectangular. If we need to go back from rectangular to cylindrical, we use this second set. This is just Pythagorean identities, right triangle trigonometry. Do you remember how much r squared is? If r is the little radius, the hypotenuse, if you will, how much would it be? R would be the square root. But r squared would be x squared plus y squared. We also know a couple other things. Tangent theta, we always define this as, well, sine over cosine, but if sine is the y and the x is y over x, and then, hey, how much is z? Z is z, because there's no change there. This is how you would go from rectangular to polar. Or, sorry, cylindrical. Same thing. A couple notes. We got a couple examples. Literally, the only few things I want you to do is this: be able to translate back and forth from rectangular to cylindrical, from rectangular to spherical. We haven't got there yet. From cylindrical to spherical, from spherical to cylindrical. And then be able to change some equations from rectangular equations into like cylindrical or spherical into rectangular or cylindrical into rectangular. Be able to do that stuff. Just translate it. And you know what? It's going to use this stuff. That's it. We got a couple more for spherical, but it's literally just translation. Being a little clever at times, but literally just translation. There are a couple notes though. Please note. Important. Please. R. I'm going to write all of it down, but I'm going to say it first, okay? R is not the distance from the origin to the point. R is the distance from the origin to the projection of the point on the xy plane. That's what R is. I'm going to draw it for you in just a second, but I want you to write it down first so we get this in our heads. R is not the distance from the origin to the point. R is the distance from the origin to the projection of the point on the xy plane. R is polar, which means R can't travel outside of the xy plane. R is in that plane, which means that R can only go from origin to somewhere on that plane. The only thing we can do on that plane is project the point on that plane. That's what R gives us. So R is not the distance from the origin to the point, it's the distance from the origin to the projection of the point on the xy plane. It's kind of a big deal. And the reason why it's a big deal is because when we get to spherical, we have something that is the distance from the origin directly to the point. That's a different type of coordinate system there. It's called spherical. One more thing. This is a big deal. We're about ready to translate between like rectangular and cylindrical, and cylindrical and rectangular. You got to make sure that your quadrants and your octants match up. Because a lot of times we can get these two different, especially when we're going from rectangular to cylindrical, we can get two different thetas. We'll say, hey, you're rectangular, you get this tangent of 2 pi or tangent of 2 pi over 3. What is that? Well, you got that one, but if I say tangent inverse of -1, there's a few values that you can get out of that. Does that make sense? For that reason, you got to make sure that when you're changing your coordinate systems, that you're matching up your quadrants and your octants. So I'm going to put that down here. You'll see exactly what I mean in a couple examples, but match your quadrants and octants when you're converting points. I'd like to show you a picture of how cylindrical actually works, then we're going to start doing some examples. So here's how this stuff works. If we have this point floating out here in space, this point floating out here somewhere in space. Do you guys see where I'm trying to represent that point? It's like it's floating out here. Okay, I'm going to ask you two questions. Firstly, what octant is that point in? Can you visualize that? It's an octant 1. The projection is in quadrant 1. Do you guys see the quadrant 1? Quadrant 1, quadrant 2, quadrant 3, quadrant 4 of the XY plane. Do you guys see what I'm talking about? Here's what cylindrical does. Instead of going, oh, here's X and here's Y, and where they meet, that's XY, and then here's Z. This is still the Z, but polar takes over for that plane. So polar says from the positive x-axis, you get me? There's an angle from the positive x-axis, from the origin to the projection of that point. That angle is theta. That is what that is. Here's the big one that people get kind of messed up on. The R. The R does not, please look at the board here real quick. I need your full attention, okay? R does not go from here to here. That is not what R does. R is polar. That's all R does. So on the XY plane, like flat on the XY plane, what theta does, it sweeps out the angle, man, from the positive x to where the projection of the point is. So you're looking at it from like the top, and you go, hey, take that point. It's going to look like it's flat. Make sense? Where it looks like it's flat, whatever angle from the positive x, whatever that is, that's theta. However far the origin is flat distance on the plane, from the origin to the projection of the point on the xy plane, that is what R is. Show of hands if you understand what R is. That's R. When we get to spherical, this distance is going to be called rho, the Greek letter for R, standing for radius. That's what that's going to be. So we can't get R and rho confused. I need you to know which one is which. You guys okay with what I'm talking about? The Z, it's still the height, just like any other height. It's just the height that that actual point is above the XY plane. Do you guys understand the idea of this cylindrical coordinate system? So we have R. R is the distance between the origin and the projection of the point. Theta is that angle from the positive x-axis until we reach the projection of the point onto the xy plane. Z is still just the height. I messed up my theta. Let's go ahead. Let's try to translate here real quick. So I'm going to give you some, and I have to basically tell you what they are. I'm going to give you cylindrical coordinates right now. We're going to translate that to rectangular. We're going going to change this to rectangular. Man, if I can't get you to do anything else, I want to get you to at least visualize where this is, like on a graph. So, number one, what's the R? Can you tell me what the R is here? It goes in order of R, theta, Z. What's the R? Write down all the stuff you know. Please do that. What's the theta? And the Z? Now, visualize where it is and write that down too. So visualize where that is. So look at the board here real quick. This has an R of 3, which means I'm coming out here 3 units from the origin, flat on the plane, 3 units, and then my angle, where's my angle? Negative. So from here, I'd be going this way. Do you guys see what I'm talking about? You got to pretend like you're looking down at it. I'm going down, negative angle. I'm going this way. So this is going 3, negative angle. It's over here somewhere. And then is it going up or is it going down? Where's it going?
Up.
Then it's going to shoot up here a little bit. What quadrant would the projection be on?
4.
Perfect. What octant are we in? 4, and then we drop down 5, 6, 7, 8. Okay, so we are in quadrant 4. We're also in octant 4. Does that make sense? Write that down. The reason is, and not necessarily going from cylindrical to rectangular because you don't have any option there. It's going to be one thing. But going from rectangular cylindrical, you get options for the theta. You absolutely have to match up the quadrants because you can make some mistakes here. So anyway, let's give it a try. Let's go over here and see. If we're going from cylindrical to rectangular, this is the only stuff I have to use. So let's see if we can fill it out. If I want to get x, x is always, no matter what, r cosine theta. Hey, do you get an r? That's why I write this stuff down. Do you have a theta?
Yes.
That's all you need. So we're going to have 3 times cosine of negative pi over 6. For goodness sakes, please do not freaking give me decimals, ever. Square roots and fractions, all right? Unit circle, people. Tattooed, right there. That's what I want to see. Someday, I really do want to see that. Just, even Hannah, I know. I want it like a legit, but whatever. I'll take Hannah. If it's on your skin, you can't cheat. It's there, right? So, okay, can you figure out what 3 times cosine negative pi over 6 is? Because if you can, that will give you the x-coordinate. What's cosine of negative pi over 6? Do you know?
It's 3 squared.
Is it positive or negative?
Positive.
Positive. Hey, would you look where the point is? Do you see that it's going to be here, right? And that's projection. X has to be positive. It has to be. Cosine is positive in quadrant 4. Oh, we're in quadrant 4. That's why we think about these things when we write them down, so we don't make negative, positive mistakes. That's why we think about where it is. So this is going to be 3 times, what did you say it was?
3 over 2.
3 times root 3 over 2. Let's try the y. The y says we're going to do 3, still the r sine theta. So we have the same exact numbers, except we have a different trig function. How about 3 times, what's sine of negative pi over 6? What was that?
Negative 1/2.
Negative 1/2, because in quadrant 4, sine is negative. We're in quadrant 4, negative. So negative 3 times 1/2, negative 3 halves. With me? Tell you what, there's a hard one coming up, but I'll handle it for you, all right? Z, I know, it's ridiculous. I'm going to take a wild guess. Pretty sure. Hey, yeah, no, I'm just joking, but do you have an x-coordinate? Do you have a y-coordinate? Do you have a z-coordinate? You now have a rectangular point. That's how you change from cylindrical to rectangular. It's literally plugging numbers in. It's literally just polar to rectangular, the same thing. So our point now is that. Just make sure we're in the same exact quadrant, same exact octant. So we're going to check it out. Does And I don't care exactly where it's at, just make sure our quadrants match up and octants match up. This is our x, that's our y. Our x says positive, our y says negative, and our z says positive. That puts us in the same quadrant on the plane, and it puts us in the same octant when we have a 3D coordinate system. Show of hands feel okay with that one. That's the idea. Tell you what, we're going to move a little quickly here because that idea, it's exactly the same every single time. Every time. What I do want to do is go from rectangular to cylindrical. You guys ready to do that? So let's try that. Any questions at all? Because I'm going to work over here. Anything at all? Okay. So rectangular, I'm going to give you square root of 2, negative square root of 2, and 4. And I want to change this to cylindrical. Hey, number one thing, man, when you're converting this, you got to make sure what quadrant and what octant you are in right off the start. So let's think about where that's at. If we draw a little separate picture here. We're in rectangular coordinate system. Just give yourself an approximation. Is my x, what is it? Can you identify my x, my y, and my z? Because if I'm in rectangular, I should have those things. Can you identify it? What is my x, please? And my y?
Negative.
And my z?
4.
So back to like 11.2 when we first started plotting points. We first go x, would I go positive or negative along the x?
Positive.
So I'm out here somewhere, okay? I don't care exactly where, just somewhere. Would I go positive or negative along the y?
Negative.
So I'm going to go this way. Does that make sense? I'm still in the xy plane. I am in quadrant what?
4.
Beautiful. Do you guys see the quadrant 4 I'm talking about? Whatever we get, we better make sure we match up with quadrant 4. And then from there, am I going to be going up or down? So I'm like here, somewhere over here. I'm right there. I'm in quadrant 4. I'm in octant 4. You sure you're okay? You're making eye contact. All right. Are you sure you're okay? Sure. Not too bad, but you have to visualize it. It's kind of weird. You're in 3D, right? So we're positive x, negative y, positive z. We're in octant 4 for sure. Let's translate this to cylindrical. If we want to go from cylindrical to rectangular, we got this. Plug in thetas and r's, you get x, y, z. If I want to go from rectangular to cylindrical, I'm going to have x, y, z's, and I want thetas and r's. So we're going to have to use this stuff. Let's plug it in. So the first thing I notice is that r squared equals x squared plus y squared. So r squared equals square root of 2 squared plus negative square root of 2 squared. Now you're liking those square roots, right? I know. How much do we get? All said and done, how much do we get? R squared equals what? Hopefully you got 4. Did you get 4? Okay. What do you do next? How much does R equal? How much does R equal?
2 plus 2.
No, it's not
Plus
2.
or minus 2. Plus or minus.
Plus or minus 2. We're going to talk about that. It's plus. No, normally, like typically 99.9% of the time, just take that one and you'll be fine. Take the positive 2. But I want to show you why we have that and why we consider that one. Are you guys okay on that one? Most people, you just go, yeah, just pick 2. Fine, whatever. Keep it positive. Hey. But we'll talk about why we get 2 different angles and how that works with this. Okay? So next part. We got an R. What's the other thing we need? Come on, quickly. What is it?
Theta.
Theta. Whenever we talk about thetas, we have this. Tan theta equals y over x, which means tan theta equals, man, I gave you nice ones. Negative square root of 2 over square root of 2. How much is negative square root of 2 over square root of 2? Negative 1. from there, you're fine. You can do it from there. Or if you want to do the theta, how do you find theta from right here? Come on. Can you tell me right now, and here's the deal. When we talked about polar, when you first did it, theta can go from 0 all the way to pi over 2. It has the whole range there. So can you give me two values of theta for which tangent is -1? Or in other words, tan inverse of -1, you're going to have two values there. We don't restrict it to that negative pi over 2 to pi over 2. We can go outside of that because we're on that plane. So how much is theta? Cosine and sine have the same values, but one's negative. Come on, that's quadrant 2 or quadrant 4. Are you with me on this?
Yes.
What is it?
3 pi over 4.
3 pi over 4 or?
7 pi over 4.
Head nod if you're okay with that one. So again, if you want a little side note, keep in mind that theta goes from 0 to 2 pi. It is the entire plane. So we have 2 pi. Now wait. This is cool. If you didn't understand anything before about why we even did this is why we do this. What quadrant? I know we talked about quadrants, like why we're in 3D. What quadrant were we in?
4.
Which one of these is in quadrant 4?
7 pi over
Then pick that one. Pick the one in the correct quadrant, okay? My bad. Pick the one in the, dang it, it's really hard. In the correct quadrant. This is not in quadrant 4. This is in quadrant. We're going to talk about that one. We're going to talk about it in a little bit. So, yeah, there's two of them, but only one is in the proper quadrant. This is in quadrant 4, where our point is in quadrant 4 on the xy plane. Do you guys see the dilemma that we have here going from rectangular to cylindrical? We have these two, we've got these two angles pretty much all the time. Match the correct quadrant to the correct quadrant. That's what we want to do here. So, what's the cylindrical coordinates for that point? What do you think? Well, let's see. I want to be out here, whatever the r is, 2. I want to be going all the way around, 7 pi over 4, and I want to go up 4. So we have an r of 2. We got it. R of 2. What puts us in quadrant 4, everybody? What is that one? And what puts us at the appropriate height? Oh yeah, z is z. So what is it? Now I know there's a question hanging out there somewhere. What's the question?
If 2 is positive or negative.
What's the question? What about that one? What's that do? I want you to understand that that's a valid answer, and so is this one. Please listen. If we went to 3, please watch. If we went to 3 pi over 4, we would be right there. Do you guys see it? 3 pi over 4. If we went out a radius of -2, do you remember what radiuses of -2 do with polar? They go, yeah, here's your angle, but then you reflect it 180 degrees or pi. That puts you back in the correct quadrant. So here's the whole big shebang. Match up the positive radius with the correct quadrant, gives you a correct interpretation. Match up the negative radius with the opposite quadrant, and it also gives you a correct interpretation. You just need to know which one to match up. Positive radius, correct. Boom. I'll put your huge note down there for this one. Use the positive radius with the theta that is in the proper quadrant. that also, obviously the corollary is use the negative radius with a theta from the other quadrant, the non-proper quadrant, and it works out for you. I really, really want to know if I've made this make sense to you. If I give you on a test, hey, let's go from rectangular to cylindrical, can you do it?
Yes.
Yeah. That one's not too bad. You got to watch out for your thetas. If I say go from cylindrical to rectangular, can you do it? That one's really easy. It almost never fails. You just plug the numbers in. You're pretty good. Show of hands if you're okay with that one. One more little side note. This is pretty cool because you can do tan inverse of -1. Listen, if you ever get down to here and you go, hey, tan inverse of -13/5, just leave it, please. Then this goes right here. That's still an angle, but you put tan inverse of nasty thing that's not on your unit circle, it goes right there. Okay, don't approximate it, don't decimal it, just put tan inverse of nasty thing that you can't find. Make sense? But if you can find it on your unit circle, for heaven's sakes, you need to put it down correctly. Okay, show your hands if you're okay with that one. Okay, so, take back. Now we're good to go. That's literally it. That's literally it for cylindrical. What we're going to do right now is we're going to talk... Easy? I told you it's about the easiest thing. You're probably getting bored. I'll make it harder. All right, we'll talk about spherical. It's not hard. It's the same stuff. We're going to talk about spherical. Spherical does use the distance from the origin to the point, and it defines it not as r because that's not what that means. It defines it as this thing called rho. That's Greek for r. So it talks about radius. So it uses the distance from the origin to the point. I don't write very good rows, but that's about what rho looks like. Like that. That's a better one. That's a lowercase Greek letter rho. Think radius. Think radius like it would be on a sphere. Radius goes from the origin to a point on a ball, and that's what this is doing. It's going out from the origin to some place on an imaginary ball, like a unit ball, but it doesn't have to be a unit. Now, some other cool things. It uses theta. The theta is used in spherical just like it's used in cylindrical. It's still going to be this distance to the projection of that point. That's what this is. So it uses distance. Uses theta just like cylindrical, but then it has this other angle. And we call it phi. So this angle phi, what this angle does, this angle is from the positive z-axis to where that radius, that rho is. It's the angle from positive z to where the segment that would connect the origin to the point, rho, where that actually is. Now, I do want to talk about, you probably can picture it right now, but if I'm talking about an angle from Z to my point, Z is this line right here. So as soon as I get to here, that would be pi over 2. Does that make sense to you? This would be like pi over 6, pi over 4, pi over 3, pi over 2. As soon as I get to pi, I can't go any further, because if I go further than pi, I'd be able to measure it from this way. Does that make sense to you? So it's from positive z, no matter where you're at. So this phi is always between 0 and pi. It does not go past pi. Also, since rho is a distance, it doesn't work exactly like r. Rho we take to mean that it's never negative. Rho is always defined as being positive. So rho is positive. Theta has exactly the same interval. And now phi has to be between 0 and pi. And what we get is this sort of a picture. We still have this angle. We still have this distance here, but we don't define it in spherical. What we do have is the same exact theta. So the theta is still the angle from the positive x-axis to where the projection of that point is in the xy plane. It's still that same angle. We don't have a z anymore. What we do have instead is a rho. The rho is the distance from the origin to the point, like direct straight shot radius. And then we have this guy. From the z, positive z, not negative z, positive z to where that rho is, that is what phi is. Head nod if you're okay with that one. By the way, if I did want to define it, what would that guy be? That would be r. Do you see that this distance, if this is parallel to this, if this is right from here, do you see that that distance is the same as r? I'm going to use that to define a couple things. You see, we got to have some ways to translate between spherical and rectangular. So we're going to do a little proof. It's not hard. It's a little proof here. So here's what we know. Actually, you know it. Come on, quickly. What's x equal in terms of r's and thetas? What's it equal? And what does y equal, please? But there's more. See, there's problems. If I'm going to spherical, I can't have any r's anymore. Do you see what I'm talking about? I need rhos, I need thetas, and I need phis. So we got to translate from r to rhos and phis. And here's how we're going to do it. Watch carefully. If you blink, you're going to miss it, okay? Check it out. Let's talk about r. If I'm talking about r, my distance from here to here is rho. My angle from here to here is phi. So if I'm talking about r, that's opposite. Just think of the triangle here. That's opposite over hypotenuse. What gives us the relationship of opposite and hypotenuse? And if I solve for r, we get rho sine phi. Do you guys see how we get rho sine phi? No? If you don't see it, here it is. Sine phi is opposite over hypotenuse. Do you guys see it? Multiply by rho. Boom. R equals rho sine phi. So now if we substitute that, well, hey, x is r cosine theta, r is rho sine phi. Y is r sine theta, r is rho sine phi. So now we have x equals, looks nasty, rho sine phi times cosine theta, and y becomes rho sine phi times sine theta. These can get awfully hard to remember. They really can, especially the different phis and thetas. You write the wrong one and they screw it way up. That happens to me all the time. But here's how I always think about it. I think about x as r cosine theta because that's like burned into my head and I can't get rid of it, all right? It's like you click on the wrong thing. Oh, no, just whatever. But it's there. You can't unsee things. Or I can't unsee, that's in my head. This one's not. So when I think about x, I think about r cosine theta. And I go, well, what's r? R is the rho sine theta. Why? Because I have a picture of this in my head. And go, okay, this is r is the opposite over hypotenuse. That gives me the r and the sine aspect of that. Does that make sense to you? So here we got r cosine theta and r sine theta. It's the same stuff. We now just defined what r is. It's rho sine theta. Sorry, rho sine phi. So if fans feel okay with that. There's only one more that we got to do. You see, this stuff doesn't have z's in it. It's not going to have z's anymore. What we're going to have to find is, well, a way to translate that. So how we translate from z's, let's say. I'm going to be given this height as z here. Well, this would be z. How does z compare with phi and rho? Think of the right triangle again. Come on. What would take z and rho and put them together with phi? What trig relationship? This is the adjacent.
Cosine.
That's the hypotenuse. Cosine. Do you guys see the cosine I'm talking about? So if I'll do it for you. If cosine phi would equal adjacent over hypotenuse, if I solve for the z, we got rho cosine phi. I want to know if you're okay with those ones. Are you? Now, how would you use it? Would you go from rectangular to spherical or from spherical to rectangular here? You plug in all the spherical stuff, it's going to give you x's, y's, and z's. This is how you go from spherical to rectangular. How do you go back? Well, we got kind of something pretty nice here. We know that the equation of a sphere, what a sphere looks like, is radius squared equals x squared plus y squared plus z squared. Since we have spherical coordinates, that's going to allow us to translate back from rectangular to at least the row aspect. Take a square root and good. By the way, when you take the square root, you only consider positive rows. Unlike the r, you only consider positive rows. We think of this as a true radius. It is always positive. But then we also had that theta. What's nice about the theta, it's literally the same theta. So you have tan theta equals y over x. That's the same thing. The only other one is this one. If we use this and solve for cosine phi, we're going to have z over rho, and that's the way we get back to our phi. And that's how we're going to go back from rectangular to spherical. The examples are actually pretty quick, but I want to make sure that you guys understand at least the idea of what these look like. And not if you do, you feel okay with that one. So the way spherical works again, it still has this theta. It no longer has a z. It's got a distance straight from origin to point, and it has this other angle telling us our aspect from the positive z-axis. All of the spherical coordinates are written in this format. Now that we understand all this stuff, here's how they're written. We've always written rho, then theta, then phi. Rho, theta, phi. Tell you what we're going to do. We're going to do two examples. We're going to translate from spherical to rectangular. We're going to translate from rectangular to spherical. We're going to take our break, and when we come back, we're going to do some special ones. We're going to translate from stuff like cylindrical to spherical, or spherical to cylindrical. It actually gets easier. It's not harder. It's easier. And then we're going to start talking about translating some of these equations from like rectangular to spherical stuff. America. Booyah. I don't know. We're going to do that. So after we get back, we'll do some of that stuff. It's not hard. You just got to be a little clever sometimes. So we'll talk about how to be clever with equations. Would you like to do a couple of these at least twice? One from one way, other way. Then we'll make it funner when we get back. It's going to go quicker because I don't have to explain anything. It's just working through it. So that'll be nice for me. So it really matters, right? These can be a little challenging for some people to visualize what's going on. So when we take a look at where this is, again, you got to have a picture of where this guy is quadrant-wise, octant-wise before we get going. So what do these things mean? What's the 3? Come on, quickly. What's the 3 mean? What is that? If this is in spherical, which I have to tell you that, what is the 3? What's this one? Is that phi or is that theta? What is that? Theta. That is theta. Okay, check it out. I want you to visualize this. If your row is 3, that means I'm coming out. I've got a radius of 3. Got a radius of 3. So let's imagine it this way. What's the theta going to do? Is it going to move it this way, negative, or this way, positive? So it's going to put it right here. Do you guys see that? So that's in quadrant what? Okay, but now I also have that phi saying from the positive z-axis, I'm coming down here 3 pi. Stop me when I get a 3 pi over 4. So I'm coming down here. How much is that? It's like pi over 4. What would it be on the xy plane? It'd be pi over 2. And if I keep on going, I'm going to be at 3 pi over 4. If I get all the way down here, that would be pi. Does that make sense? Can you visualize that this thing is below the xy plane? I guarantee you, any phi value, legitimate this in your head here, any phi value past pi over 2 is going to give you a negative z. Do you guys see that? At pi over 2, you're on the xy plane. Past that, negative z. Before that, positive z. Past pi, you can't. You can't. Does it make sense to you? Visualizing it helps a lot. Let's go ahead. Do you guys want to try it? You want to try changing that to rectangular?
Yes.
We have some stuff that shows us what to do. If I want to go from spherical to rectangular, we're going to plug this stuff in. So x equals, well, you know what? We'll do 1. We'll do the x together. I'll give you the y and the z on your own. What's the first number I should plug in if I'm doing x? What is it?
3.
3, because the row is 3. And then x says, well, x is r cosine theta. I know that's what x is. So in my head I'm thinking, okay, r is rho sine phi. But then I have to have that cosine theta because x is r cosine theta. I've got to have a cosine theta up there somewhere because I'm talking about x. You guys see what I'm talking about now? That's how I memorize it, so I can always get that cosine for x. I want that in my head. Cosine theta for x. You sure you're okay with that one? Are you at all good at your unit circle stuff?
Yes.
Perfect. Sine of 3 pi over 4. All students, sine has to be positive. 3 pi over 4, it's root 2 over 2. Cosine pi over 4. Cosine pi over 4, that's in the first quadrant. Root 2 over 2. Which means that we get 2 over 4, it's 1/2, times 3. Looks like we get 3/2. Can I get a double check on that work? Try the y, try the z. Go for it. Also, you're going to see this. I mean, hey, it's the same r, right? X is r cosine theta, y is r sine theta. So you're going to have the same exact thing here and here. Take advantage of that. Is it okay to get the same coordinates twice, like x, y? Did you get the same coordinates twice? Did you get 3/2? Still okay with it? Can you find the z? Did you understand that the z has to be negative for sure, like for real? If we're going past pi over 2, you're going to be below the xy plane. You're going to have a negative z. So z is r and cosine, because that's the adjacent. Man, I really want this picture in your head, because if it's in your head, you see that the z is part of cosine, and it's part of phi. You see it. Do you guys see what I'm talking about? Z, the height. It's the cosine part of the phi. That's where it's coming from. One of the worst things is to have to do a test and do all this stuff and really not get it. And you just, oh man, my formulas, where's my formulas? What's going on? I lost my formulas, oh crap. If you get the picture, like you understand how cosine and sine works, you can recreate this stuff. And it becomes easier. It becomes easier going, hey, yeah, I actually get it. Cosine, phi, relates z with rho. Oh. Then z, I can get rho cosine of phi. That makes sense. Sine relates r with rho and phi. That's how these formulas are created. They're in your head. You understand it better. Sorry, I digress. 3 times, what is cosine of 3 pi over 4?
Negative.
Oh my gosh, negative, just like we wanted. So 3. Do I have an x coordinate?
Yes.
Do I have a y coordinate?
Yes.
Do I have a z coordinate?
Yes.
So we write the rectangular. We're gonna verify that this is in the proper place. This was in quadrant 1, but octant 5. So this guy went out 3 pi over 4, but down like this. That's where that went. This is also in positive x, positive y, negative z. It's also in quadrant 1, but that octant 5. That's where that thing is. It's the same octant, same quadrant, so I know that we got it right. Show of hands, feel okay with that one for real. Be sure. X, positive, y, positive, z, negative. So out, and down. This one went, you got this thing floating around, right? But it's pi over 4. And then this pushed it down past the xy plane into octant 5. That's where that is. It's hard to draw these things really accurately, but I want a picture in your head at least. That's what I want. We're going to go backwards, and then I'm going to let you, we've got to take a break after that one. So let's go from rectangular to spherical. Okay, we're going to move on this one, all right? First thing I want you to do is whatever coordinate system I give you, write down the pertinent information. If I give you rectangular, you got x's, y's, and z's. Please right now write down the x's, y's, and z's. Next up, understand where I'm trying to get to. If I want to go to spherical, I've got a way to do that. Now, obviously, going from rectangular to cylindrical is a piece of cake. It's a lot easier. But spherical, we also have some stuff there. So if I'm going from rectangular to spherical, I got to take my x's, y's, and z's. You know what that is? It's a gall-darn magnitude of pretty much a vector. Because that length from the origin to a point would be the same exact thing as a magnitude of it's a magnitude. That's all we're doing. Square the stuff, add them together, take a square root. That's how we find our row. Does that make sense to you? So let's do that first. So to find our row, oh, you know what? I forgot something. I forgot the major part. Before we even do any of this work, what's important about it? What should we be thinking about at least?
Where is it at?
Where is it at? What quadrant is this in? Negative x pushes us back. Positive y comes up this way. What quadrant? Quadrant 2. And then positive z pushes us up this way. What octant?
2.
So we're in 2, 2. So quadrant 2 on the xy plane, octant 2. Floating right about there. It doesn't have to be exact. So let's go ahead, let's find our row. So to find the row, we're going to take the square root of x squared plus y squared plus the z coordinate squared I think it's 4 root 2. I'm pretty sure. Square root of 32, 4 root 2? No?
Yeah.
Double check.
Yes.
Triple check. You got the same thing I got? Use calculator, whatever. What else do we need? Come on, quickly. What else do we need? We got a row. All these things are a row, and then we got... Can we find our theta?
Yes.
How?
Equals x over 3 y over x.
10 theta. You're right. Y over x. Don't do x over y. Do y over x. Rise over run. Y over x. So then tan theta negative square root of 3. Tan inverse of, man, do you know tan inverse of negative square root of 3? Do you know that one?
So 30?
Give it to me in terms of pi. Pi over 6? So let's see, we want the square, we want sine over cosine, right? And we want the square root of 3 to be on the sine part and the 1/2 to be on the cosine part. And we want it to be negative. So we want the signs to be wrong with each other. So what would it be? Well, it's got to be in either quadrant 2 or quadrant 4. Do you guys see what I'm talking about? Quadrant 2 or 4. I know that cosine of pi over 3 and 2 pi over 3 is that root, is that 1/2. So I want the denominator to be 1/2. So this has to be 2 pi over 3 or 5 pi over 3. It's unit circle time, folks. We don't have time to function around with this. We don't have time to F around with it, sorry. But you have to know how to do that. Honestly, I don't want decimals. I don't want 30 degrees. Calculus is done in radians. We need radians, and I want them in radians, and I want them accurate every freaking time. Sorry to be a jerk, right? But I want it done because I want you to be successful at it. I want you to get down to here and be like, I don't know. Why don't you know? Print out a unit circle. Tattoo it. Right there. Just draw it. I don't care. But I need this like up here. Are you following what I'm talking about? I need that. Now, man, there was something huge we talked about. It was, you better make sure that this stuff matches where this is. And we did it. What quadrant on the XY plane is the projection of our point? What quadrant's that in?
2.
Which one of these is in quadrant 2? That one, not that one. You only pick one. There's no two options here. You pick the one in the correct quadrant. So since our projection of our point is in quadrant 2, that angle for theta from the positive x is also in quadrant 2. It's right there. That's the appropriate theta. That's how you do it. There's no doubles here like there was in cylindrical. That's the only one. Show of hands if you feel okay with that one. Yes, no? Yeah? Yeah. Or this between that, because that's this one from here to here we go. That's the one it is. Okay, so unit circle says tangent of what angle gives us negative square root of 3. That's where sine is either positive or negative, and cosine is positive or negative, but you have different signs. Sine has to be root 3 over 2. Cosine has to be 1/2. That only happens at 2 pi over 3 and 5 pi over 3. It's only two places it happens. There's only one right answer, though, because only one of those is in the correct quadrant of the xy plane. Only one, and it's that one. That's it. Now, let's talk about cosine phi. Do you recognize, like in the formula, that in order to actually do this, you have to find rho first? You can see what I'm talking about? You have to be able to find that first. So once you find rho, that's the first thing you do. Then you find theta. You just hang on to that a little bit, and then we go down, we find phi. So for phi, we're going to put z over rho. Of course, you're going to simplify it. So simplify the 4's, rationalize, we got root 2 over 2, and you get a nice one for once. Thank goodness. What is cosine inverse of root 2 over 2? And keep in mind, there's only one answer here, because this is only defined from 0 to pi. We don't go past that. So you don't even have to worry about all the other stuff. It's literally just between 0 and pi. And since cosine is 1-to-1 between 0 and pi, we go, hey, sweet. I love that. Cosine just drops like this. It's a 1-to-1 function from 0 to pi. There's only one answer. So you have to get pi over 4 and nothing else. Does that make sense to you? Let's also verify that. This was in quadrant 2, but it was also in octant 2. It didn't go below the xy plane. This isn't going to go below the xy plane. It looks right. Double check your work. Have the picture in your head. It makes it a lot nicer. Then we're going to do one more thing. We go, okay. So if you want the little side note here, remember that that's the interval for phi. Doesn't go outside of that. And we put the spherical coordinates. How do we start it off? What do we put first? The rho, the phi, or the theta? What's first?
Rho.
What's the next thing that we do?
Theta.
Theta, which is, what do we get on that one?
2 pi.
And then we wrap it up with our phi. It'll give you the same point. It's just two interpretations, and that's what we're talking about. Show of hands, feel okay with this one. We're gonna take a little break right now and come back. Okay. All right, back at it. Some quick examples of how to go between like cylindrical and spherical, spherical and cylindrical. Honestly, these become a little easier because they're more related than, say, spherical to rectangular, which there's no relation. So going from everything we have and use this stuff to do any translation. Let's talk about cylindrical. And I want to go to spherical. Cylindrical to spherical. The number one thing I want you to do, please write down the stuff you know. So if I'm in cylindrical, your mind has to shift a little bit, and you got to tell me what these numbers actually mean. You got to know what that 4 actually is. What is that 4? That's not an X because I'm not in rectangular. What is that 4? That's an R. Are you guys making that shift in your head? That's an R because I have cylindrical. That's the R, the projection of the distance from the origin to the point, the distance from the origin to the projection of the point on the XY plane. What's that? What's that?
Theta.
And since we are in cylindrical, what's that?
P.
We're in cylindrical, so that is still Z. I'm going to see if you're paying attention right now. We're about to change to spherical.
No.
I want to know, yes we are, I have it important, for sure. What I want to know is your phi. Is your phi going to be more than or less than pi over 2?
More than.
Negative Z, more than, here's the xy plane, more than or less than pi over 2?
More.
It's got to be more than. Because I'm going into the negative part, it's got to cross the xy plane, it's got to be more than pi over 2. It's got to be more than pi over 2. Head nod if you're okay with that one. Are you sure? That's what's happening. So let's translate it. Can we go from R's and Z's and thetas into stuff like, well, what I want rho, I want theta, and I want phi. Which one of these guys do we already have?
There.
So I already know that spherical I'm going to get pi over 3 for sure. I know that's going to be there. Now, as far as the rest of it, you're going to be using some of the same stuff, but there's going to be pieces that relate these two. Oh, I forgot one. Sorry. There's going to be things that relate this. So for instance, you go, well, maybe I need rho. That's the only thing that's solved for rho. Let's use that. However, I just finished telling you, a lot of this stuff, it gets easier when you're doing this for this reason. Check this out. Yeah, I know that this is x squared plus y squared plus z squared, but think carefully on it. What is x squared plus y squared? That's r squared. So this formula gets a little easier. This really becomes r squared plus z squared. Hey, do you know an r? What's the r? Quickly, what's the r?
4.
Do you know a z? Can you plug those things in? Let's plug them in. Let's solve for phi. I get 4 root 2. You guys get the 4 root 2? Yeah, we can the 4 root 2. I know I'm doing a lot of math fast in my head, but I want to know if you understand where this stuff is coming from. So man, you don't. Some of you guys aren't even paying attention now. I want to know if I'm getting through to you. Do you understand that the theta, that is not going to change between cylindrical and spherical? That's going to be there. I have the same stuff. The r and the z, yeah, we're going to have to use that. And one way we use that, if rho squared is defined as this, well, x squared plus y squared is r squared. Use that. That makes it even nicer. Man, you got to plug in 2 numbers. Plug in the 4, plug in the negative 4, square them, add them, take a square root. It's going to be 4 root 2, so I've already calculated that one. Now, what about the phi? There's really only one thing up here that deals with phi and being able to solve for it. Well, 2 things. You could use one of 2 things. You could do cosine phi z over rho, which that's the one I prefer. You could actually do that one, because you could do sine of phi equals r over rho. And since you're given r, either one of these is going to work just fine. It's just the other way of looking at that right triangle that we already talked about. Does that make sense to you? Pick one. I don't care. As long as you're getting something that's going to solve phi. I'm going to use this one, but as long as you're getting something that's going to allow you to solve for phi based on the information you're given. So this says negative 4 over, hey, I just found the rho. We talked about how to find phi. You got to find rho first. Can anyone out there tell me, on the interval of 0 to pi, because we cannot go outside of that, It's got to be from 0 to pi. What would give us, cosine of what angle would give us negative root 2 over 2? I know it's an over 4 because these are all over 4. Is it pi over 4 or 3 pi over 4? Because there's only those two options. It's 3 pi over 4. It's kind of nice because we don't have those two options. There's no way to make a mistake. You can't go outside of 0 to pi for phi. So there's only one choice there. And because theta's already given, there's no choice there either. It's literally given to you. That's pretty nice because that's kind of the hard part, right? Is knowing quadrant, match up the quadrant, pick the right angle. You don't have to do that between cylindrical and spherical or spherical to cylindrical because theta is always given for both of those things. You guys see what I'm talking about? Show of hands if this made sense, you feel okay with it. So we had R, yeah. We had Z, yeah. Theta, given, no problem. We use our any formula that you can, as long as it relates to this information. This changes to R squared plus Z squared, plug it in, we get 4 root 2. After you find this, use either this or that one, either one. I chose the cosine phi. We had our Z, you have to find rho first in either case, but then it becomes just you look at the unit circle, make sure for phi that you do not go outside of 0 to pi, and then you're going to have that correct. So that's our spherical coordinate for that point. Let's go backwards. Let's go from spherical to cylindrical. Okay, the two ideas I want you to do, the first idea is if ever I give you a type of coordinate system, I want you to write down what we have. Like, write down what it is, and then also now write down what you need. So right now I want to know if I give you spherical, goodness gracious, what does that number mean? What is the 5? R, X? I don't know, it's probably one of those. What's this one?
Rho.
It's a rho, because spherical starts with rho. Everyone in class, right now. What's that?
Theta.
And that one? If you've got an angle last, you're probably in spherical. It's the only one that does that. Okay, now, right-siders, just you guys, I want to know what you need for cylindrical to work. How is it organized? I know it's 3 things, but what are those 3 things? What do we start with? So we need an R. What's the next thing that we have? Left-siders, what do we have? Is that going to be nice for us in this? Yeah, it's easier. And then the last thing we have is what? Z. So right now, I know that theta, pi over 4, done. This is actually going to be the easiest thing that we've done today, I'm pretty sure. Do you have a formula up there that's solved for R? Do you got a formula up there that's solved for Z? Do it. Go for it. I'll give you about a minute maybe. Go ahead and do it. Man, just make sure you plug in the right angle, right? There's 2 to choose from. Make sure that we are talking about phis right now. Oh, hey, how about this? How about this? When we get to the Z, and you do 5 cosine 3 pi over 4, if that angle, if that phi is 3 pi over 4, Would you expect a positive z or a negative z?
Negative.
It should be a negative z. If we don't get that, then we've made a mistake. You guys starting to see the idea here. You can check your work if you understand the concepts. 5 times, oh my gosh, sine of 3. What is that?
Root 2.
Root 2. You just need to know it's positive because that's second quadrant. Root 2, it's all students. It's positive over there. So that's going to be 5 root 2 over 2. The z, I'll bet you it's going to be negative. Since this is negative root 2 over 2, we get negative 5 root 2 over 2. I would really love to know if I have made sense to you today. I do want to talk about this. Just one little blurb. Doing this, you cannot possibly get a negative r. You can't possibly get it. And I want to show you why. If you talk about this is how you get r, correct? Please watch carefully. This is how you get r. Rho is always positive. You with me? Always. Sine phi, well, phi can't go past pi. Sine is always positive from 0 to pi. All students, remember 0 to pi, sine is always positive there. So if sine is y is always positive in the first 2 quadrants, that is always positive from 0 to pi. Therefore, positive times positive is going to give you positive. You don't have to worry about getting negative r's. It won't happen. So you always get positive r. This guy, yeah, that you don't have to worry about it at all. You just take the same exact thing here, and then this, it's only from 0 to pi also. So when you're going on that cosine for the first pi over 2, so we're dropping, right? First pi over 2, you're positive. Next pi over 2, you're negative. And that's how these things actually work. Are you sure you're okay with it for real? Any comments, questions at all? This part, I actually like this part. We're going to start talking about how to translate between different types of equations. So I give you an equation like this. R equals 3. And you go, awesome. What does that mean in terms of a 3D picture? What is it? What's that mean? It says, well, firstly, maybe you can tell me what coordinate system it's even in. Would you say that's rectangular?
No.
You see a whole lot of x's and y's and stuff? Is that spherical? Do you see a whole lot of rhos and phis? What is that? That's cylindrical. It's what? I'll give you probably the biggest hint here. Anytime you have a variable equal a constant, you basically have the type of shape that the coordinates are based on. So if r is cylindrical and it's equal to a constant, you have a cylinder. That's what you have. This is a cylinder with a radius of, what do you think? Geniuses, all of you. Yeah, exactly right. Now, where is it going along? It's going along the z. Now, how do I know that? Well, the thing is, that's pretty nice to describe a cylinder, isn't it? But we're not used to it. Because mostly when we think about these pictures, they're all in x's and y's and z's and stuff. You know what I'm talking about? That's what they're in. So I know it's a cylinder, I know it's radius 3, and I know it's along z. How can I prove it? How we prove it is by making this stuff out of this thing. For instance, if I square both sides, you guys see that r squared equals 9, yeah? Square both sides. Square both sides. Oh, but wait. R squared is this. You guys see how to get there? Oh my gosh, this is in 3D. How many variables you got? 2. This should be exciting. How many variables you got?
2.
What's that mean? Surface or cylinder?
Cylinder.
Going along what axis? The z with a radius of 3. Just like that. Radius, same stuff. We're used to this, so we typically have to translate it. But look at the ease of the formula here. Man, that's so much nicer to work with. So if you understand that, when we get to double integrals and you have to define what the cylinder is, that's an easier way to do it. That's why we have this stuff, is to make those connections. How about this one? world is that? Crazy. What in the world is that? Well, that could be either thought of as cylindrical, because it's got that phi, or spherical, because it's still got that phi. But that phi is constant. So what it's saying is this. From the positive x-axis, I'm going out, what'd I say? Phi, fo, fum, whatever, theta. It doesn't matter. In my head, I was saying theta. It didn't come out that way? Dang, I'm getting tired. Okay, so theta, edit. So the theta, it comes out from the positive x-axis, pi over 4, and then it's fixed. What's that do? If you have a fixed angle and any points along that, that's going to be a plane. A plane at the angle of pi over 4. I guarantee it's a plane. How can you prove it? Well, I know that tangent theta equals y over x. So tangent of pi over 4, our theta is pi over 4, has to equal y over x. But I know what tangent theta is. I know tangent pi over 4 is. I know it's 1. And if I solve for y equals x. Okay, now stick with it. How many variables you got? It's a cylinder, a really crappy cylinder called a plane, okay? It's going along the z-axis, but it's just y equals x, it's that line, and then it's going right along the z-axis. Do you guys see what I'm talking about? That's kind of cool. That's what this is. Which one's easier? That one. It's because it's equal to a constant. Let's talk about one more like this, and then we'll do some tougher ones. Okay, real quick, what in the world is that thing? What is that thing? Would that be rectangular or cylindrical or spherical? What is that? Spherical. Obviously spherical because, whoa, I'm palpitating a little bit right there. Easy. You get a heart attack. I'm already excitable, man. I have way too much caffeine and candy. Whoa, that's a double whammy. So it's obviously spherical because we got that row in there. Listen. Okay, that's 2. You're trying to kill me. Anytime you have the base thing of your coordinate system equal to a constant, you have the thing. So if I'm in spherical coordinates and that's equal to a constant, that is a sphere. That's a sphere centered at the origin with a radius of, what do you think? 2. How do I know? Same thing that we would do here. So sphere, radius 2, centered at the origin, for sure. Let's square both sides. Oh, but wait. X squared plus y squared plus z squared equals 4. That's the definition of what a sphere is. In fact, if you want to put it in standard form, just divide by 4, you got square plus square plus square equals constant. You guys see what I'm talking about? It's square plus square plus square, all squared. All pluses equal to a constant. That's an ellipsoid. However, it's an ellipsoid where all the denominators are the same. Ellipsoid spread out equidistant from the origin creates a sphere. That's a sphere centered at the origin with a radius of 2. Which one's an easier formula to work with? Oh my goodness, that one. It's got one variable. That's really nice. So when we get to stuff like triple integrals and we have to integrate over spheres, you're going to use that because that sucks to work with in an integral. You can picture it. It's not fun. So that's what we're using this stuff for. Now, some of them, man, they're not that obvious, honestly. These, I mean, maybe like, that's not obvious, man. Well, at least there's something there. Okay, you can get there. Sometimes we get some really not obvious ones. That's what I really want to work on right now. This should be okay. I really want to work on these ones. Because these ones really don't look very nice, and they're not readily apparent, like what in the world this thing even is. So when that's the case, when it's not obvious what they are, that should be obvious from now on. That's a cylinder. It's pretty obvious from now on that's plane. That's pretty obvious. That's a sphere. But from here on out, if it's not obvious, convert it to rectangular. Convert everything to rectangular. If it's not obvious, convert to rectangular. Why? Because we already have rectangular stood up in our heads. Does that make sense to you? I don't want to switch everything, just kind of the easy ones. So when not obvious, convert to rectangular. using anything you can. Don't change out variables that are good for you. So for instance, z's are pretty good for me for rectangular, don't change these. R's are pretty easy to change, so I know r squared, use parentheses, is x squared plus y squared. Make it a little bit prettier. In fact, what I would do is I'd add this to both sides. Well, no. Yeah, it would. I'd factor it so it looks like something we started our day with. Do you remember that shape at all?
Hyperbolic.
It's obviously a surface. This is either a paraboloid or a hyperbolic paraboloid. Why? How many squares you got?
Two.
Two of them. And you have one that's not square, but these are both pluses. Come on, hyperbolic paraboloid or paraboloid?
Paraboloid.
It's paraboloid. Where? What? Along what axis?
Z.
Opening towards the positive or negative?
Negative.
Negative and shifted up 4. Yeah, so this is shifted up 4 on the Z, opening this way with pictures of circle. Pictures of circle on the XY plane is what that looks like. That's what it is. Just like that. Can you see this better than you can see that? Yes. You guys understand how to get from here to here? That's not the hard part, but I want you recognizing the shapes. I know you haven't practiced it yet, but I want you recognizing the shapes. Some of them look really hard. You got to kind of be a little bit tricky, on this stuff. So r secant theta equals 4. This doesn't look good. I have nothing that I don't want to start putting square roots up there. You can do things like this. Okay. First thing, try to get sines and cosines. 'Cause I don't see a secant anywhere up there. So what I know is that this is r times 1 over cosine. If I multiply by both sides, or on both sides by cosine, it looks a little better, but not way better. And then you go, here, how about this one? I know that I like cosine as long as cosine has an r in front of it. I know I like r's as long as they're square. Let's multiply both sides by r. These are things that you can do. Tell me right now, what is r squared in terms of x's and y's? What is that?
X squared.
How much is r cosine theta? Hopefully it should be burning your head. How much is r cosine theta? You guys okay with that one? Multiply both sides if you can. Be creative with this stuff. As long as you're not dividing out, well, multiply whatever you want. As long as you're doing the same side. That's okay. Square both sides, it's fine. Now, do you know what that is? How many variables do you have? So I guarantee it's got to be a cylinder. For sure, got to be a cylinder. Now, what's it look like? That takes a little bit more math magic here. So we do things like x squared minus 4x plus y squared. We do things like complete the square. We did it, I think, one of the first days of class. We get something at least a little bit more identifiable. Is it still a cylinder?
Yes.
It's traveling along what axis, please? And this is a circle with a radius of 2, but it's shifted, shifted along the x-axis. How's it 2? So on the x-axis, we're coming out 2, making a circle, and then right like that. It's a soda can that's been shifted away from the center. It's actually going to touch the origin because it would radius 2 and it's shifted away 2. It's going to touch the origin. It's going to be right along the Z. but that's what that picture. Are you starting to see them in your head? I don't get time to draw, man. I don't have time for that. But I want you to at least see them to understand that's a cylinder along the Z. It's got to be a circle with a radius of 2, and it's also shifted positive x-axis 2 spots. It's pretty cool when you can do stuff like that. Let's try as many as we can in the next about 10 minutes, and we're going to be good. For things like this, try the same exact technique that we used for this. So when you have rows and you want row squares, and you have cosine phi's and you want row cosine phi's, try doing things like multiplied by a row on both sides. And then we get some nice stuff. I know rho squared is x squared plus y squared plus z squared. I know that this is Z. You guys okay with that one? What shape do you think that is? What shape do you think that is? Yeah? How about now? What shape do you think that is now? What do you think it is? If anything, that's an ellipsoid. If anything, that's an ellipsoid because, hey, all squares, all pluses equal to a constant. But look at it. Look at it. Are all the denominators the same? What's an ellipsoid? Where all the spreading out stuff is the same. What's that called?
Sphere.
That's a sphere. It's shifted up 2 spots on the Z axis. Are you guys starting to see it? This is a ball that is floating right on the XY plane. It's got a radius of 2. It's shifted up 2 spots. So think plane, XY plane, ball. It's sitting right on there because the center shifted up 2 spots. It's got a radius of 2. That's what's happening here. So if you guys feel okay with that one. Which one's easier to identify? That. It's not easier to work with though. That's easier to work with. But you can visualize that better. So it's a trade-off. Yeah. Oh, we got like 3 more of this. 3 minutes. We can do it. What is the first thing that you would do on that problem? This is nasty, man. Nasty. I'd clear those also. You're gonna like this one. You're gonna like this one. You're gonna like this one. Tell me right now, what is that? Or, what's the whole thing? Do you see that that's R?
Yeah.
And that's cosine R, cosine theta is? What is x equals 2? What is x equals 2 on a 3D coordinate system? What is it? It's a plane. It's floating here, x equals, it's just a plane. Which one's easier? That's way easier. Because when you start talking about rectangular figures, rectangular's easier. Spherical figures, spherical's easier. That's why we have these different coordinate systems. That's describing a plane at x equals 2. It's what that is. Just a plane. That's it. You're welcome. Tell you what, we're going to do 3 more examples. I hope to. I want to. We'll try. Are you going to kill me if I do? Oh, man. I'll run. I'm a fast runner. Well, I used to be. I haven't ran in like 8 years, so I'm imagining it's still true. That's what happens, right? So what is that? Oh, it's obviously a one-sheet hyperboloid along the z-axis. Duh. How do you know? Because you do things like, hey, let's find some stuff that looks familiar here. This right here, if rho sine phi is, well, let's see, r, then this is r squared. If rho cosine phi is z, then this is z squared. You guys catching the picture here? Use that stuff. But wait, I want rectangular. What's r squared? Quickly, how many variables? All squared. One negative with a constant, what is it? One sheet hyperboloid along the z. Well, do I know what it looks like? No, I'd have to do a little more work than that. But at least I know what the shape is. It's this hourglass along the z. That's what I know. Are you picking up what I'm laying down? Told you they're quick. Don't worry. Just stay hang with me. We're gonna have some fun, man. I got more candy and everything. All right. These are weird ones. They're kind of cool though. They're kind of cool. When you get some weird stuff, they're like, wait, all R's, but it's factorable. If you can factor it correctly. Do you follow the factorization? Basic algebra, but in this context, it's pretty freaking cool. Now, we just covered one a little while ago. What is R equal 1? It's a cylinder. What's R equals 2? This describes two cylinders. One of them, and along what axis? The z-axis. Cylinder with a radius of 1, centered at the origin, going along the z. And then another one, cylinder, radius 2. It's like a toilet paper roll, all right, where you get the inside and outside. That's what it looks like. It's not filled in, but it's those two cylinders. That's one inside the other. Isn't that kind of cool? That's what that describes. Two cylinders. Just for fun. Just for fun. Can you give that to me in cylindrical and then spherical? If you have to do both, do cylindrical first, I'm begging you, because it's like a halfway step. Do cylindrical first. As long as you have R's and Z's and thetas, you're done. That's what cylindrical is. And then go to spherical. So for instance, so this is, oh, by the way, what would you categorize as that? Rectangular, cylindrical, or spherical? It's obviously rectangular because there's only x's and y's. Do you know how much x squared plus y squared is? Use that. Goodness gracious. If it's a minus, you got a little bit more work to do because then you got to do the whole this and that. Does that make sense? You got to do that stuff. But if you got something nice, and then y. Y is r. Right there. Use the same stuff you used right here. Start dividing by r's. That's okay. That right there is a cylindrical equation. It has only r's and thetas in it. So this would be cylindrical. Is that okay with you? Now, spherical doesn't have r's, but it can have thetas. So it's just a little translation more. This is like a halfway step. Do I need to change the sine theta? No, don't worry about it. Do I need to change the r? Yes. Yeah. Okay. Oh, that one. Done. That's spherical. Get rid of what you don't want. If I'm trying to get cylindrical, I don't want x's and y's. I want r's and thetas and z's. If I'm getting to spherical, I don't want r's and I don't want z's. So we got to translate those pieces that we don't want out of the equation. Is this clear enough? I want to make sure that we do. Is it good enough that you understand it? I have one more. I really don't want to go over it because it's almost exactly the same thing that we have. It's just translating into r's and rows and other stuff. Hello, yes, no. Show of hands feel okay with the topic. Easy, medium, hard. What do you think?
Easy.